Good morning, students. I am Meenakshi Gurjar, Assistant Professor of Chemistry. Today's our topic is HSAB theory part 3. In last two videos, we have discussed about HSAB theory part 1 and part 2. In these videos, we have discussed about principle of HSAB theory and classification of acids and bases as hard and soft. Okay. Now, in this video lecture, we will focus on application of HSAB principle. First, in hydrogen bonding. We know that the strong hydrogen bond is possible in cases of H2O, ammonia and HF. Since the donor atoms are oxygen in H2O, nitrogen in ammonia and fluorine is in HF, hydrogen fluoride. We know that these donor atoms are hard Lewis bases and their interactions with partially positively charged hydrogen, which is a hard acid, are stronger. You know, in Pearson HSAB concept, always hard entity, its mean hard acid will always combines with hard bases and soft acid always combines with soft bases. And you know that FON, these donor atoms act as hard Lewis base, and hydrogen H plus acts as a soft H plus acts as a hard acid. Then combinations of these hard acid and hard Lewis bases are will be stronger, and we can explain hydrogen bonding in this way with the help of HSAB principle. Second application of HSAB principle is linkage of ambidentate ligands to metal atoms. You know what is the ambidentate ligands? Ambidentate ligands means a ligand which can bind with both atoms. It's mean SCN negative. It is an example of a ambidentate ligand. Here two donor sites are available. First is sulfur and second is nitrogen. This acts as a ambidentate ligand, but it depends on the metal ion. You know that sulfur atom acts as a soft base, whereas nitrogen atom acts as a hard base. When hard metal acts when hard metal reacts with it, then it's bind towards nitrogen end, and when soft metal bind with this ambidentate ligand, then sulfur end will bind towards this metal. The ambidentate ligands SCN negative can bind either by sulfur end or nitrogen end. The bonding mode can be determined by using HSAB principle. It bonds through sulfur atom. I have told you sulfur atom acts as a soft base when bonded to a platinum plus 2. Pt plus 2 act as a soft acid. This metal ion acts as a soft acid. Then SCN negative thiocyanide bind with sulfur atom, and however it bonds through nitrogen atom, which acts as a hard base when linked to a Cr plus 3 chromium plus 3 metal ion, which act as a hard acid. So we can explain linkage of ambidentate ligands to metal atoms with the help of HSAB principle. Now comes on third point, inorganic reactions. HSAB principle is used to predict the outcome of some of the reaction. Look at here, AsF3, arsenic fluoride, when react with phosphorus iodide, then this reaction goes forward direction. It's mean arsenic iodide and PF3, phosphorus fluoride, comes. You know that in AsF3, F negative acts as a hard base, and Pi3, in Pi3, I negative acts as a soft base. And we know arsenic and phosphorus both are softer. We know that in table we have in table of HSAB, which I told you in last video, arsenic and phosphorus both acts as a soft acid. But you know that arsenic is softer comparatively than phosphorus. So arsenic is more softer comparatively than phosphorus. Then arsenic combines with iodide ion, and phosphorus combines with fluoride iodide. Fluoride ion, and this reaction completes in this manner. Second is, the following reaction is possible since Mg plus 2 is harder acid than barium plus 2 and oxide is harder base than sulfide. MgS. MgS, in magnesium sulfide, Mg plus 2 acts as a hard acid, whereas S minus 2 yani sulfide, it means sulfide acts as a soft base. In barium oxide, Ba plus 2 acts as a soft acid and O minus 2 acts as a hard base. So, according to HSEB principle, hard complex will be more stable and soft complex will also be more stable comparatively than hard soft and soft hard complex. So MgO, which is a hard complex, and barium sulfide, which is a soft complex, will be more stable, and this reaction goes forward direction. Other application is precipitation reactions. Precipitation reactions, the softer acids like Ag plus, Hg plus, Hg plus 2, etc., and borderline acids like as Fe plus 2, Ni plus 2, Cu plus 2, Zn plus 2, and Pb plus 2, etc., can be precipitated as sulfides from their aqueous solutions since sulfide ion is a softer base. You know that these metal ions always precipitated in the form of sulfide. Why? The reason behind this is that these metal ions acts as softer acids and sulfide ion acts as a softer base. According to HSAB principle, soft complex will be more stable. So these metal ions always precipitated in the form of sulfides. Okay. This is the last application of it, relative stabilities of complexes in aqueous solution. HSAB entails that tetracyano-cadmium complex is more stable than tetraamino-cadmium ion. According to HSAB principle, hard prefers hard and soft prefers soft, Hence the soft acid Cd plus 2, here Cd plus 2, you see here in both complexes metal ion is same, cadmium plus 2, Cd plus 2, and in both complexes ligand bases are different. In first complex for cyanide ligand, and in other complex, in second complex, NH3 acts as a ligand. Ligand means it acts as a base. We know that cyanide ion acts as a soft base, whereas ammonia acts as a hard base. And we know that Cd plus 2 is a soft acid. So soft complex will be more stable according to HSAB principle. So cadmium CnCN4 minus 2, it means tetracyano-cadmium complex will be more stable comparatively than tetracyano-cadmium ion. It is clear from the K instability constant, where cyano complex has instability constant is 1.4 into 10 to power minus 19, while for amine complex it is 7.5 into 10 to power minus 8. We know that instability complex in case of amine cadmium complex is high comparatively to cyanide complex, so cyano complex will be more stable. Okay students, these are the applications of HSAB principle, and these applications we can explain with the help of HSAB principle. Now till these videos we have completed our first unit HSAB. Okay, thank you.